All right, so today we are talking about stoichiometry, and I'm giving you a note-taking guide. Stoichiometry is a big, long, nasty word, but it's not as scary as it sounds. All right, so the purpose of stoichiometry is there are two purposes. Number one, you could use quantities of reactants to predict quantities of products. So what I mean by that is, if I begin with X amount of A reactant, how much B product could I make? Right? That's a question that a chemist would take some benefit from, right? If I begin with 5 grams of reactant, how many grams of this product could I make? That's a useful question, right? Just like if I'm making cookies and I've got this amount of reactants, i.e. ingredients, how many cookies am I going to make, right? That's a useful question. So use quantities of your reactant to predict how much product you're going to make. And then likewise, use quantities of products to work backwards to determine amount of reactant that was used. So for instance, if I do an experiment and I determine that this amount of product was made, I could work backwards, figure out how much reactant I used in the first place. Or maybe I want to make 5 grams of product. Work backwards. How much reactant do I need to begin with if this is the amount of product I want to end up with, right? So for instance, to put it into baking terms, if I want to make 6 dozen cookies, how much flour do I need to begin with, right? So if I begin with 4 cups of sugar and 5 cups of flour and XYZ amounts of all your other ingredients, how much cookies can I make? Or, going the other direction, if I want to make this many cookies, how much reactant do I need to begin with? All right, so that's what stoichiometry allows us to do. We can use the quantities of reactants to figure out how much product that's going to give us. Or, if I know I want to make a certain amount of product, work backwards, how much reactant do I need to begin with? Does this make sense? And this is useful in, baking, but it's also useful for us in chemists in the lab. So that's what stoichiometry is. It's a series of calculations. And it sounds scary, and it's kind of got a bad reputation because it's a scary sounding word, but it's not a difficult concept if you just pay attention to what you're doing. So here are the steps in stoichiometry that we're going to go through. Write a balanced, must be balanced chemical reaction. That's step 0. Just like when you're baking, step 0 is get the cookbook, right? You gotta have a recipe. Step 0 for a chemist is you gotta have your recipe, right? The balanced chemical reaction is your recipe. If I'm gonna make a bundt cake, I don't know how to do that off the top of my head. I've got to go find my cookbook, right? If I'm going to do a reaction in the lab, I obviously need to have the balanced chemical reaction in order to give me a guideline of what I'm doing. All right, so step 1, convert grams to moles of your starting material. And I say starting material because the starting material could be reactants, but it could also be products, right? If you're working backwards, your starting material would be a product. If you're going reactants to products, then obviously your starting material would be reactant. So that's why I say starting material, because starting material could be a reactant, it could be a product. It just depends on, are you going reactants to products, or are you going backwards, products to reactants? So convert grams to moles of your starting material. Then you're going to take that answer, and you're going to multiply it by the mole ratio, which is the coefficients of the balanced chemical reaction. Right? That's why you need a balanced chemical reaction, because otherwise step 2 of stoichiometry won't work. It's not going to happen. So you're going to convert grams to moles of your starting material, and then you're going to multiply that number by the mole ratio, and this is going to be a fraction, okay? And then that'll give you your finishing material. This will give you number of moles of finishing material. And again, I use the generic word finishing material because if you're starting with a reactant, your finishing material will be a product. But if you're starting with a product, your finishing material will be a reactant. That's why I just use those generic words, because I don't want to use reactant and product, because you may not be using a reactant to calculate product. You could be using a product to calculate reactant, going backwards. Okay? So this will give you number of moles of finishing material. So step 3 is then convert moles to grams of finishing material. Because 99% of the time, this is an experiment you're going to do in the lab, which means you're going to be measuring mass. You can't measure moles. Right? You don't have a moleometer, but you do have a balance that you can go measure mass on. Okay, so that's why grams are involved. So, things to think about. When you're converting grams to moles, are you going to use Avogadro's number or molar mass? Which one do we use there? Avogadro's number is only used when the problem involves what? Atoms, particles, right? Is that part of this? You see the word number of particles, number of atoms anywhere in here, right? So make sure you note to yourself, in step 1 and step 3, you're using molar mass, not Avogadro's number, okay? Because Avogadro's number is only used when you're dealing with number of atoms, number of particles, number of formula units, right? We're not seeing those words anywhere in here. We're only dealing with masses and moles, which means we use molar mass. So if you don't already have a periodic table out, go ahead and take a second, fish one out, because you're going to need it today. So, get a fresh marker so that the camera picks it up nicely. Is everyone okay if I erase these steps? Okay. Let's go through the process. All right, here's an example. I'll zoom the camera out just so we can read it, and then I'll zoom it back in. Ammonia is produced from the reaction between nitrogen gas and hydrogen gas. If you begin with 20 grams of hydrogen gas, how much ammonia can you make? All right, so step 0 is we need what? A balanced chemical reaction, right? So it is, if I say ammonia is produced, does that mean ammonia is a reactant or ammonia is a product? It's a product, right? And it's a gas as well. It's produced from the reaction between nitrogen gas. Okay, so what's the formula for nitrogen gas? N2, good. Remember, nitrogen as a gas is diatomic. And hydrogen gas, what's the formula for it? H2. All right, we produce NH3. Give myself some room to put coefficients in here. All right, so is this balanced? No, it's not. Do we want to make a reactant and product table, or can we do it in our head? Let's just do the table just for practice. N, H, N, H. We've got 2 and 2. We've got 1 and 3. So let's deal with the 2 and 3, right? Because if this is a 1, that's easy to fix. Can I turn a 2 into a 3 or a 3 into a 2? No, but I can turn them both into what? 6. So if I want to turn this into a 6, what do I do? Multiply the whole thing by 2. Right? 6, 2, and then if I turn this into a 6, 3 there. Okay. So if you still need help balancing equations, make sure that you take some time to go practice that skill using the worksheets that I have on the course page or the suggested problems in the textbook. Because if you can't balance this equation, step 2 of stoichiometry is going to be a train wreck, right? Because you have to have a balanced chemical equation. All right, now what I do is I read the problem and I say, okay, it's got 20 grams of hydrogen gas. So I write that underneath it. So that I don't use my information in the wrong place, okay? 20 grams of hydrogen gas, so just write that underneath it. So in other words, do I care about this at all? Is this going to factor in my calculations at all? No. We're pretending that I've got an unlimited amount of N2, but I've only got 20 grams of H2, okay? And the question is asking, how much ammonia can you make? So put question mark grams there. Okay, so N2 isn't factoring into my calculations at all, right? This is just H2 going to NH3. So step 1, we're going to convert grams to moles of my starting material. So 20.0 grams H2. If I'm converting grams to moles, where does grams go, on the top or on the bottom? On the bottom, right? And moles goes on top. 1 mole of H2 has what mass? Is it 1.008? Or is it 1.008 times 2? You multiply by 2, right? Because it's H2. So 2.016 grams. Does everyone see where this number came from? Molar mass of hydrogen times 2, right? Because it's H2, not just H. Now, in terms of your sig figs, our final answer is going to need 3 sig figs. So let's carry out extra digits here and round at the very end. Because if I round here and then round at step 2 and then round again at step 3, my answer is going to be rounded too much. Either too much up or too much down, just depending on how much you round. So carry out extra decimal places and we'll round at the end. So 20 divided by 2.016. Grams cancel. Left in moles. So that gives me 9.9, let's just say 9.921 moles H2. Carry out extra decimal places, round at the end. Because if my final answer is going to need 3 sig figs, I should have at least 4 in my rounding steps. Okay, because then I'll round at the very end. So that's step 1. Everybody good with this? This is just grams to moles. Now we're going to take this number, we're going to rewrite it. So step 2, 9.921 moles H2. So this is the mole ratio step. This step converts you from this unit to this unit. And this is where the mole ratio comes from. So I say to myself, okay, I want H2 to go away. So it goes on the bottom. And I want to turn it into moles of NH3. Right, because that's the substance I'm interested in. And now I'll look at the equation. For every 3 moles of H2 that I use, I produce 2 moles of NH3. So do you see where these numbers come from? That's just the coefficient from the balanced equation. And you only do this at step 2. You don't do it in step 1. You don't do it in step 3. It's only a step 2 problem. Because now moles of H2 cancels out and I'm left with moles of NH3. And this is how I convert from H2 to NH3. So I take my answer, multiply it times 2 and divide it by 3. So times 2 divided by 3. And again, carry out extra decimal places because we're going to be rounding at the very end. So this gives me, let's just round, 6.614 let's do 4. Mole NH3. Does everyone see how we did step 2? Mole ratio comes from the coefficients of the balanced chemical equation. So that's moles of NH3, but do I have a really easy way to measure moles? No, right? Can't measure moles in the lab. That's not something I'm able to do. What's something I can measure in the lab? Grams, right? Grams, that's something I can measure. So take this number and rewrite it. You're going to do one more conversion. So 6.614 moles NH3. Now I'm going to convert that to grams, because grams is a unit I can measure easily. So if I'm converting to grams, does grams go on top or on bottom? Grams would be on top, right? Because that's the unit I'm converting to. And mole would be the unit I'm converting away from. So 1 mole of ammonia has what mass? Well, you have to calculate this molar mass, right? It's not just sitting on the periodic table. I've got to calculate it. So 1.008 times 3 plus 14. Right, that's where we get our molar mass. So 17.024. So moles goes away. I'm left with the unit grams. So times 6.614. So my calculator spits out 112.596, blah, blah, blah. I can only keep 2 sig figs, right? So what is my final answer? I'm sorry, I can only keep 3 sig figs. So what's my final answer? 113. Questions on this problem? Now, this is assuming I've got an unlimited supply of N2, right? In these problems, we don't know how much N2 we have. We're just assuming it's an unlimited supply. In a minute, we'll talk about problems where we know exactly how much N2 we have and exactly how much H2 we have. And then that's a whole different kind of problem. I mean, it's still stoichiometry. You just have to approach it from a slightly different angle. But let's start with the easier ones first, and then we'll worry about the more difficult ones. It's not more difficult, it's just more work. Questions on how we did this one? All right, on the back, there's one for you to try. So I'm going to erase this. So here is one for you to take a crack at. When 15 grams of oxygen gas reacts with hydrogen gas, water vapor is produced. How much water is formed? I'm going to pause the recording and give you a chance to try that one. All right, let's go over this one. Oxygen gas and hydrogen gas producing water vapor. And we want to know how much water vapor we can expect. So first we need a balanced chemical equation. What's the formula for oxygen gas? O2. And what's the formula for hydrogen gas? H2. And then water vapor is H2O gas. Is this balanced? No. What do we need in order to balance this? We need a coefficient of 2 in 2 places. Where? In front of H2. And where else? In front of H2O, right? All right, we're told it's 15 grams. And we want to know how much water vapor we're going to get. So again, we're assuming we've got an unlimited supply here, or a very, very large quantity. So let's go through our steps. we've got 15.0 grams of O2. Let's set up our conversion factor. Grams goes on top or on bottom? Bottom. So grams, moles. 1 mole has a mass of 32 grams, right? Because 16 and 16 is 32. So 15 divided by 32 gives us, let's carry out a couple extra digits because we're going to be rounding at the end to 3 sig figs, so we need to have at least 4 in our intermediate steps. So let's go with 0.4688. Okay. Now we're ready for step 2. So let's take that number, 0.4688 moles O2. For every 1 mole of O2 that I use, how many moles of water vapor am I making? 2, right? So 2 moles of H2O. So moles of H2O goes away. I mean, moles of O2 goes away. I'm left with moles of H2O, so I take my answer and multiply by 2 times 2. So that gives me 0.9375 moles of H2O. Do we agree there? Now we're going to take this number and convert it to grams. So 0.9375 moles H2O. Now we're converting to grams. So 1 mole has a mass of 18.01 grams. Right? That's the molar mass. So times 18.01. That gives me 16.884, blah, blah, blah. So what does that round to when I round to 3 sig figs? 16.9. All right, 16.9 grams. How do we feel about this one? If you made a mistake, do you see where you made it? Yes. So like I said, it's not difficult, it's just 3 steps, right? You just have to do 3 different calculations. Questions on this one before we go on to limiting reagents? So far, we've just assumed that the amount of H2 we had was either unlimited or very, very large, right? But now let's look at a situation where I have a restricted amount of this one and a restricted amount of this one. What's that going to do for me? So that's where we have to start looking at limiting reagent. And that is on the next section of your note-taking guide. Stoichiometry versus limiting reagent. All right, if you know information about more than one substance, you must determine which one you'll run out of first. I use that quote marks, right? It's not very scientific. So for example, you could think about this in terms of baking, right? In baking, if you only have 1 cup flour, but 20 cups of sugar, right? Who cares if I've got 20 cups of sugar? If I've only got 1 cup of flour, I'm probably not baking very many cookies, right? This is the ingredient I'm going to run out of first. And if I'm out of flour, I'm not making any more cookies, right? So you have to figure out which ingredient are you going to run out of first. The ingredient that you run out of first, that ingredient is called the limiting reagent. Okay? Reagent just means reactant. And limiting, obviously, because it limits how much you can make. So LR stands for limiting reagent. In limiting reagent calculations, do the math, i.e. the stoichiometry, twice. right? Twice. You're going to do it for each reactant. Go from A to B for reactant number 1, A to B for reactant number 2, and then compare, okay? You compare the products, or the results, I should say, because if you're going backwards, you'd be comparing the results. And pick the smallest number. The smallest number. Because think about it like this. If I am doing my limiting reagent calculation using my baking, and I say, okay, if I assume that I've got 20 cups of sugar, I can make 60 cookies. But if I have 1 cup of flour, I can only make 10 cookies. Well, which answer is correct? 60 or 10? 10, right? Because once I run out of that flour, I'm done making cookies, right? So it doesn't matter if my 20 cups will allow me to make 60 cookies. I'm running out of this 1 cup really quickly, so I'm only going to actually make, what did I say, 10, right? You do the calculations twice for this big number and the smaller number. And by the way, let me just throw this out there. The smaller number is not always the limiting reagent, because limiting reagent calculations are based on mole ratio and molar mass. And that's where baking deviates from, chemistry. Because when I'm baking, I'm not dealing with mole ratios here. I'm not dealing with molar masses. If the molar mass of this one is significantly huge, this one might be the limiting reagent. Okay? So don't always assume that the smaller number is the limiting reagent, because a lot of times it's not. A lot of times the bigger number is the limiting reagent, because remember, it's based on mole ratio from the balanced equation, and it's based on molar mass. So if this thing's got a monstrously huge molar mass, and this one's got a tiny molar mass, this one might be the limiting reagent. So you can't just assume, okay, 1 is less than 20, therefore this is the limiting reagent. You can do that in baking, because baking, we don't care about molar masses. But as a chemist, we are not allowed to do that. All right, so when we do our calculations, you do them twice. You pick the smaller number, and then the limiting reagent. The limiting reagent is the substance that gave lowest amount of product. The excess reagent is the substance that gave the biggest amount of product. And the theoretical yield, whatever this number ends up being, that value goes right here. Okay? You pick the smallest number. And theoretical yield is just that. It's what you should get theoretically. If you go do the experiment. Now, if stoichiometry tells me, all right, I expect to make 5 grams of product, does that guarantee that I'm actually going to get that 5 grams when I go in the lab and do it? No, what's that going to be contingent on? That's contingent on me, right? If I'm really sloppy and I dump over my beaker and I spill my product and I sneeze in my beaker and a whole bunch of other bad stuff happens in the lab, that's my fault, right? Stoichiometry says, hey, this is how much you're supposed to get, but it's not a guarantee that you're going to actually get that, right? What you get in reality is based on you and, things that might happen. If you stumble over your feet on your way to the balance and you drop it, well, that's an experimental error, okay? And so one of the things that we do is we calculate percent yield, which is measured as actual over theoretical times 100. So this is the amount that you get when you actually go in the lab and do it. This is how much you were supposed to get, right? And then this is a measure of how good you are as a scientist. So in a perfect world, your percent yield would be 100, right? I was supposed to get 5 grams. Hey, look at me, I got 5 grams. Woohoo, I'm awesome, right? In reality, is it gonna be 100% yield? I guess it depends on how hard the experiment is and how good you are as a chemist, right? It's a really easy experiment that, you know, my kids could do, then, and you do it really well, then you might get 100% yield. If it's a very difficult experiment with lots of extractions or distillations or whatever, right? You might only get a 25% yield. So it's dependent on your skills as a chemist, difficulty of the experiment, and also just things that happen, right? So in a perfect world, your theoretical yield matches your actual yield. All right? So just bear that in mind, because you're going to do an experiment. You're going to do a couple of experiments where you will be calculating your percent yield, and then you'll be rationalizing that. So just FYI, if your percent yield is greater than 100, what are some mistakes that you could make that would cause you to have a yield over 100? What's something that would cause your yield to be too high? Anyone have any thoughts on what can make your yield be too high? There's one really easy one that may come right to mind if you think about some of the experiments we've done so far. Let me ask you this. If you want to know how much you weigh, do you do it when you step out of the shower and you're soaked, or do you do it before you take a shower? Right? Most people who want to be really scrupulous and go, oh, yes, I lost that extra half a pound, right? They do it before they take a shower, right? Not after when they're soaking wet. If your percent yield is greater than 100, something that could cause that would be your product is wet. Right? Think about some of the experiments we've done where you had a solid and then you filtered it, right? If your product was wet, when you put it on the balance, you're measuring the mass of the water plus the mass of the product. And 99% of the time in this class, if your yield is over 100, it's probably because it was wet. Another one, although far less common, is contamination. I mean, you'd have to have significant contamination. We're talking like you threw up in your beaker kind of contamination. Because if you've got a couple of random, you know, you didn't wash your glassware all that great, maybe there's a little bit of residue from the last person. This is not an analytical chemistry class. This is not a quantitative chemistry class. This is basically intro to how you should do things in the future, right? When you go take analytical chem, yeah, you need to wash your glassware 100 times and dry it in the oven, and then wash it 100 more times and dry it in the oven because one little particle was screw holding up. But in intro chem, we're really not all that worried about contamination, right? As long as you don't, you know, curl, you're probably not going to be listing contamination as reason your yield is over 100. It's probably because it's wet. What about if your percent yield is less than 100? So in this scenario, you've got too much, right? In this scenario, you have not enough. So what are some ways that you could have not enough? You've lost product somehow. So what are some ways that you could lose product? Spill, right? Or maybe it overboiled. We've had that happen. When you're trying to boil off the solvent and it pops out, right? If your solid's all over the table and not in your beaker, obviously you're not measuring its mass. It overboiled, it spilled. Maybe you've got a broken glass or a cracked glass and it leaked out. The reason we're going through this is because in some of the labs that you're going to be doing, you're going to be analyzing your percent yield, and I want you to explain why your yield is either too high or too low. By the way, don't just say human error, because that's just an umbrella. That means a whole lot of nothing, right? I want specifics. Well, when we were trying to boil off all the water, I noticed that there was product all over the table. That would definitely be a reason for you to lose product. Right? Do we understand the differences between having a yield too high versus a yield too low? All right, let's go through a calculation now involving percent yield and limiting reagent. So in terms of the math works exactly the same. You just have to do it 2 times now, as opposed to 1 time. All right, aluminum metal reacts with copper 2 nitrate. You begin with a 5-gram piece of aluminum metal and a 4-gram piece, 4 grams of copper 2 nitrate. What is the theoretical yield of copper metal? First thing, to make sense of our problem, we need to have an equation, right? Let's translate this into an equation. So aluminum metal, when you see the word metal, you think periodic table, right? So aluminum metal, that's just plain old Al. What's the formula for copper 2 nitrate? Copper 2, that's Cu2 plus. Nitrate, what's that? NO3 with what charge? -1, right? So when we crisscross these, we get CuNO3 2. So when you've got a metal reacting with a compound, what kind of reaction is that? Single displacement, right? So your cation becomes your new metal, and your metal becomes your new cation. So when this becomes a cation, what's the charge on aluminum ion? Al plus what? Look at your periodic table. 3. And that gets together with whatever this anion was. So when you crisscross those, you get Cu and Al NO3 3. Okay, so there's our equation. Is it balanced? That's not balanced, right? We're going to need a 3 here and a 2 here and a 3 here and a 2 here. Does everyone see how we translated this into an equation? All right, now let's write our information underneath and what we're looking for. So a 5-gram piece of aluminum metal, so that's 5 grams, and 4 grams of this. And we're only interested in the amount of copper we're going to get. Don't care about this. We're totally uninterested in that. So I'm going to move the problem out of the way now so that I've got room. So now we get to do the stoichiometry twice, right? We got to do stoichiometry going from here to here. We got to do stoichiometry going from here to here. And then we compare and we pick the smaller number. Make sense? So let's do the calculations for aluminum. All right, 5 grams. Look at the periodic table. Molar mass of aluminum is 26 point, I can't read those decimal places. 26 point what? 981. All right, so let's get started there. 5 divided by 26.981. Carry out, we're going to be rounding 2 sig figs, so let's carry out at least 3. So 0. Let's go 1853 moles Al. All right, that was step 1. Now let's do our mole ratio step. For every 2 moles of aluminum that I use, I make 3 moles of copper. Right? So I take my answer times 3 divided by 2. That gives me 0.2779. Actually, that'd be 278. Because it's 2.7797, so we'll just round out to 2.278. All right, now we got to turn this into grams. What's the molar mass of copper? 63 point something, right? Or is it 65.3? I can't remember. 65.3, isn't it? Yes, no, maybe. 63.5. I had it right the first time. 63.5 grams per mole. So times 63.5. Rounding my final answer to 2 sig figs, that gives me 17.65, blah, 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 blah. So rounding that to 2 sig figs, that would be what? 18 grams. But that's just for starting with my aluminum, right? If I had a very, very large amount of this, then that would be my final answer. But I'm not done because I have to see if this amount is going to make a smaller final answer, and then pick whichever one's smaller. Does everyone see why you got to do this 2 times? Right? Because you can't just assume that this is an unlimited or very large amount. I've got a fixed amount of this and a fixed amount of this. So I got to figure out which one am I running out of first. So now we got to do it again for CuNO3 2. Let's do this again. So we start with 4 grams. All right, molar mass of copper 2 nitrate. Let's see, we've got 64 plus 28 plus 63.5. 155.5. All right, so 4 divided by 155.5 gives me 0.02572 moles CuNO3 2. Now let's do our mole ratio step. For every, this is a 3 to 3, which is the same thing as 1 to 1, right? 3 moles of CuNO3 2, I produce 3 moles of Cu. So here, my number doesn't change, just my units. So that gives me 0.02572 moles Cu, right? Because multiply by 3, divide by 3, that's just 1. And now I've still got to convert that to grams times 63.5 grams per mole. So times 63.5. That gives me 1.6334, blah, 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 blah. I can only keep 2 sig figs, so that would be 1.6. So here, the smaller number does end up being the limiting reagent, but keep in mind, look at the differences in molar masses. 26 versus 155, right? The smaller number is not always going to be the limiting reagent. So 1.6, this is my theoretical yield. It's not a guarantee that when I go do this, I'm actually going to get that, just what I should get. So if I asked you what's the limiting reagent, this would be the limiting reagent. And if I asked you what's the excess reagent, that's just the one that means you've got extra of. This one's the excess reagent. You just do the math twice. You just have to do the math 2 times. How do we feel about this problem? I mean, it's no more difficult than the previous one. You just got to do it twice now instead of once. And that's it. All right, if you look on the next page, there are some for you to try. Well, one for you to try. In your gas grill, propane is combusted. How many grams of carbon dioxide are produced if you use 20.7 grams of propane, 37.9 grams of oxygen gas to cook your dinner? So take a second and try this problem. I will pause the recording, give you a chance to try this one. Okay, so let's go over the problem here. Propane is combusted. So combustion is a reaction with what? Right, it requires oxygen gas, and combustion of a hydrocarbon produces what?
Carbon dioxide and water.
All right. These are all gases. All right. Is this balanced? Let's make our reactant product table. C3H8O2 C1H2O2 plus 1. All right, so let's balance hydrogen. So let's use a 4. So 4 times 2 is 8. 4 times 1 is 4. And now let's do 3. 3 times 2 is 6. So that means this needs to be 5. So that I have 10. Do we agree? 1, 5, 3, 4? Balanced chemical equation? All right. So the problem says, move this down so I've got room to write. 20.7 grams of propane and 37.9 grams here of oxygen, and I want to know how much CO2 this is going to generate. All right. So let's do our calculations twice, right? We've got to do it propane to carbon dioxide and oxygen gas to carbon dioxide. So for C3H8, here we go. 20.7 grams times, let's calculate the molar mass, 1.008 times 8 plus 12.011 times 3 gives me 44.097 grams per mole. Do we agree on that molar mass? All right, so grams cancel, that gives me moles. So 20.7 divided by 44.097. So that gives me, we're carrying out at least 2 decimal places. So let's go with 0.4694. Oops, not grams. Moles. C3H8. All right, now let's multiply by the mole ratio. For every 1 mole of propane that I use, I produce 3 moles of CO2. So I take my answer and multiply it by 3. So that gives me 1.4083 moles CO2. Now let's convert moles back to grams. So 32 plus 12.011 gives me 44.011. So this gives me times 1.4083. So 61.98, blah, blah, blah. So this would be, when I round to 3 sig figs, 62.0 grams. Am I finished though? Nope, got to do it twice, right? Because I have to see, will I run out of oxygen first? Maybe I will. Let's find out. So for oxygen, so we've got 37.9 grams O2, 16 and 16 is 32. Grams per mole. So grams cancel. 37.9 divided by 32. So that's 1.184 moles O2. Now let's do the mole ratio. For every 5 moles of O2 that I use, I make 3 moles of CO2. So times 3 divided by 5. So that's 0.71. Let's just round that, 711. And now molar mass here, we've already calculated, we don't need to calculate it again, 44.011 grams per mole. So times 44.011. So this gives me 31.275, blah, blah, blah. So when I round this one to 3 sig figs, what will that give me? 31.3 grams. So which is the theoretical yield, 62 or 31.3? 31.3. Notice this was the bigger number, and it's the limiting reagent, right? So you cannot make the assumption that, oh, I just picked a smaller number and that's the one I run out of first, right? It's not like baking in that regard. Excess reagent, excess reagent, limiting reagent. And my theoretical yield is 31.3. Questions on this one? All right, I've got 2 problems for you to try. They weren't stapled into your packet. So 2 practice problems. I'm going to stop the recording here, though. So while you work on that,